Hi, this is our second unit on variational autoencoders, and I'm going to cover a few sort of surprising and strange mathematical properties of variational autoencoders. So let's review where we are. So this is a variational autoencoder. Now this version is formulated in terms of the sampling probability distribution as the main joint distribution on Y and Z. So let's remember where we are. Y is some observable data, like a sound wave. Z is some latent variable, not explicitly given in the observation, that we're using to explain it. So for example, we might have sound waves and we're trying to recover the latent phonemes and words as a good explanation of the sound waves, a good theory of the sound waves. Now, in this formulation, I'm focusing on the distribution that we're sampling from in the variational autoencoder. And it's important that we're sampling from the population. That's the thing we're trying to model. And then we've got this encoder, right? And the encoder is going to take the sound wave or whatever the observable data is and encode it as some latent variable. And then we're going to, it's a variational autoencoder. So then we're going to look at a decoding of that. So this is the distribution I'm going to focus on. This, I'm going to jump down here. This is the VAE objective function. Now, in this case, I'm writing psi for the parameterization of the encoder, and I'm writing phi for the parameterization of the other parts of the model. Now, in the standard presentation of variational autoencoders, they focus on these two pieces, a prior on Z and a posterior on Y given Z. And these two pieces together are the pieces that define a different joint probability on Y and Z, a model joint probability that's not defined directly by the population. But here I'm focusing on this, the sampling joint distribution. And there's a couple points to be made. One is that if you look at this, this is now a cross entropy. We can think of this as training a model of Y as a label of Z. We're sampling from these two variables, Y and Z, and I'm looking at minus log probability of Y given Z. So we can think of Y as a label for Z in that case, and in that, this is a conditional cross entropy. So we know that under universal expressiveness, this conditional cross entropy will converge. It will always be at least as large as the true entropy of the distribution, and will converge to the true entropy. This will become a model of the true entropy. If we look over here, and this is a log of a ratio, if we separate that, then the part that depends on P phi of Z is also a cross entropy. That's, we're basically sampling a pair YZ, but that means we're sampling Z from the marginal distribution on Z under this joint sampling distribution. And if we look at this cross entropy, the optimum of that is the actual marginal under a universal expressiveness. So this can be viewed as an approximation of the marginal onto Z of the sampling distribution. And both of these cross entropy terms are upper bounds on the entropy, right? Cross entropy is always an upper bound on the entropy. So this whole expression is an upper bound on what you would get if I stuck in the true distributions. So the true distributions the true distribution is a joint on Y and Z, and if I marginalize that onto Y, I'm getting the population distribution. So that's a completely different explanation of the structure of a variational autoencoder than I started with in the last unit. So we also can think of this in terms of rate distortion autoencoding, right? So if this is an estimate of the marginal onto Z of the sampling distribution, then this is an estimate, and it's actually an upper bound on the mutual information between Y and Z. So this would cash out as the entropy of Z minus the entropy of Z given Y, which is the mutual information. But since this is an approximation, this is actually an upper bound on the mutual information. So I'm going to call it I hat. And similarly, this is a cross entropy, which I'm going to think of as an attempt to model the entropy. like in language modeling, you use cross entropy optimization to model the entropy to try to get a handle on the entropy of English. So the VAE objective can be viewed as having these two components. One is estimating a mutual information, and one is estimating an entropy. And under the universality assumption, this is going to converge to the true marginal. So this is going to converge to the true mutual information, and this is going to converge to the true entropy. So this term becomes, if we actually converge to those distributions, this whole expression becomes the mutual information plus this conditional entropy. And the mutual information can be written as h of y minus h of y given z, which means this sum is exactly equal to h of y. So that's another way to understand why we're recovering or modeling the probability distribution over what we can observe in terms of some latent information like z. Now, I'm going to talk about some issues. So the first issue that people talk about is something called posterior collapse. So this is the thing we're optimizing. I've just written it very concisely here in terms of estimating mutual information and estimating entropy. And I'm going to consider the case where the encoder, this is the encoder distribution, right? It's taking y and encoding it as z, does something trivial, right? It just picks a single value of z and always outputs that value independent of y. And in that case, the marginal is trivial too. The marginal just has probability 1 on that one element. So this is we're considering the case of a completely degenerate encoder, right? It just does nothing interesting. In that case, the mutual information is 0. There's no mutual information between this trivial encoder and y. And in fact, this upper bound estimate is immediately 0 also, because this is trivial to model. And then what happens is, if we're modeling the probability distribution of y given z, well, y now is independent of z. So this is just the population distribution on y. So the point is that if I just optimize this naively, there exists a solution, a minimum of this expression, that has a completely vacuous encoder. So there's nothing in this expression that's preventing the encoder from being vacuous. And that's called posterior collapse, and it happens. You try to set up a variational autoencoder to extract the latent information, and the latent information just disappears. You get a trivial encoder and no mutual information between your latent variable and your observations. So this is called posterior collapse. So this is a variant that appeared in 2017 called the beta VAE. And it can be motivated in a couple ways, but the basic idea is to introduce a relative weighting between these two terms. So the VAE in general has these two terms, this mutual information and this entropy estimator. And by weighting the mutual information, I'm trying to get better control over the generator, right? Try to make the generator have more or less mutual information with y. So I might hope that by making beta small, by saying, okay, I'm going to let you have a lot of mutual information, that you would overcome the posterior collapse problem. And the original paper that introduced this said, well, was focused on the other way. So if I make beta larger than 1, let's assume we're getting some latent information z. If I make beta larger than 1, then I might drive the mutual information down, which might simplify the latent variable and make it more interpretable. So both directions sort of have a motivation. But it's interesting to note that when we, in the unit before last, we talked about rate distortion autoencoders. And a rate distortion autoencoder already has a relative weighting of a distortion term, like an L2 loss, and the mutual information. A rate distortion autoencoder is inherently trading off the amount of information about the label y being held in the latent variable, and the distortion when I try to reconstruct the original from the latent variable. It's exactly the trade-off in image compression. the rate, how big the file is, and how accurately you would cover the image. Okay, so the beta VAE is just, sort of going back to a rate distortion like weighting of the two terms. Now, one thing that's interesting, and it took me a while to realize this, that introducing beta, you might think it's changing the weight between these two terms, and it's changing the objective function. And if we optimize this, do we still have our universality theorem that if all the models are universal, we are going to recover the population distribution on Y in this framework? So it's a concern. We're changing the objective function. This is no longer an upper bound on, it's no longer the elbow. It's no longer an upper bound on the log, negative log probability of Y. However, if we look at this and assume universality, whatever psi is, when we optimize this expression, we're going to get the marginal on Z. And whatever psi is, if we just optimize this part of the model, we're going to get, and we're universal, we're going to get the entropy, the conditional entropy of Y given Z. So under universality, we're still going to get, even if we train with beta, that doesn't change the fact that this is going to be optimized at the marginal of Z. So even with beta, these two terms are going to model these two, this mutual information and this cross entropy, and these two model parameters are going to yield the population distribution on Y as the marginal over Y of these two distributions. So we get our universality theorem even after we've weighted things by beta. And this part I find the most intriguing because I haven't seen it before, and it feels like it could have important applications. And that is encoder autonomy, right? So we're focusing on this distribution. We're focusing on this distribution, and the optimization properties that I just mentioned, this universality theorem said I'm going to be universal for any psi, right? I'm going to get this property independent of psi, because I get this property as soon as I optimize these two pieces of the model, even holding psi fixed, even holding the encoder fixed. And that means that for any encoder, no matter how I optimize the encoder, as long as I optimize those other pieces of the model in that way, in optimizing these two terms, I'm going to get the universality assumption, right? I'm going to get the universality theorem that I've recovered the population distribution of Y. And what that implies is that I can add an arbitrary loss as long as it's only looking at the encoder. I can train the encoder any way I want. And all it's affecting is the sampling distribution. And the model on the prior on Z and the model of Y given Z will still encode the population distribution on Y. We'll still explain the population distribution on Y. So I can add whatever loss, whatever regularizer, or whatever loss on the encoder I want. And I'm calling that encoder autonomy. Okay, so that's a pretty short, quite mathematical section. Next time we're going to do vector quantized VAEs, and then we'll move on. Thank you.